Now let's analyze the concavity of this function using the second derivative test. Okay, we saw already that the first derivative of this function is going to be 1 minus 3x squared. Therefore, the second derivative, which is, of course, the derivative of the derivative, is going to be definitely, it's a minus 6x. Okay? And what I need to do is to find inflection points is find really where the second derivative is equal to 0. Again, I know the second derivative is a line. It's perfectly smooth. It's differentiable everywhere. So I only need to worry about inflection points are possibly at the places where f derivative of x is equal to 0. Okay? So I'm going to solve this. So solve, again, f prime prime of x is equal to 0. That means that minus 6x should equal 0, right? I'm solving this to find out where the possible inflection points occur. And I can certainly see that my solution is going to be one solution, which is x is equal to 0. So this is the candidate place where I need to check to see whether the concavity changes. Okay? And this will give me an idea of whether I have inflection points in my function. So let's draw my little number line out again to visually see what's going on. F prime prime of x. Here's my critical value of x is equal to 0. These are my x values. And what I want to know is, what is the sign of the second derivative? Because recall, again, if the second derivative of x is negative, that means that the function is concave down. Okay? Or that the first derivative is decreasing, right? The slope lines are going down. If f prime prime, the second derivative, is positive, that means the function is concave up, which again means the first derivative is increasing, okay? Or the concavity is concave up. Okay? Concave down is like a frown. Concave up is kind of like a smile. So this is kind of like this, and this is like this. Okay? With concave down functions, you know you have a maximum in that region. And for concave up functions, you know you have a minimum in that region. So let's check. This is a place. Let's look at the sign of the second derivative. So what I do is I take x values before this critical value, and I find the sign of the second derivative as a function. So if I plug some value in here, let's say -1, again, the sign will be the same for all values before that critical value. Okay? So I don't care which one I choose, just choose a value that's easy to compute. So I'm going to take that -1, I'm going to plug it into my second derivative as a function. When I plug that in, notice how the sign is positive, right? So the sign is actually positive. I get a plus 6 if I plug in -1 into this function. Meaning what I'm doing is I'm taking f prime prime of -1. That's equal to a -6 times -1, which is positive 6. Okay, so it's positive. All I care about is the sign. And again, the beauty of this is that I only need to check one place, just one point that's away from the x equals 0 over here. Okay. Similarly, I'm going to pick one place over here, pick one x value, let's say 1. Again, you choose an easy value. Take that, plug it into my first derivative. If I did that, plug it into the second derivative. When I do that, I get a -6 times 1. You get a -6. So the point is the sign is negative, which means the function is concave up over here. According to this information, right? It's concave up because the second derivative is positive. It's concave down after 0. Because the sign of the second derivative is negative. Okay? So that gives me the concavity behavior. That means the function has to have a local minimum here, right? Because it's concave up in this portion of the domain, has some local minimum. And it's concave down here, which means it has a local maximum somewhere here, right? And we already saw from a minute ago that that's what the picture of this function looks like. I already drew it for you. And let's draw it one more time. This is what's very nice about these functions. We can get a general behavior without having to resort to any sort of computing device to actually draw the function. Okay, we at least get an idea of the behavior. So recall that the function looks something like this. Here's minus 1 over root 3. Here's positive 1 over root 3. Okay, here's x equals 0, my y. And the function, it has a local minimum right at this place. A local maximum there. So remember, the function looks something like this. Okay? It's concave up here. It's a smile right here. It has some local minimum. And it's concave down over here. And in fact, it's changing inflection right here, changing concavity. So in fact, x equals 0 is what's called an inflection point. Let me write that a little bit nicer. Okay, this is an inflection point. We found out that's the inflection point because it's changing concavity from going concave up to concave down. Notice concave up, and then it changes concave down. Okay? And notice also that if we drew the tangent lines to the function, that the tangent lines are definitely decreasing here. Okay? After this critical value here where the derivative is 0, the tangent lines are increasing again. Okay? That's why the first derivative had a sign of negative here, and now it has a sign of positive over here. But all the slope lines, they're going from negative to positive, so the slope lines are increasing, which means the second derivative is positive. But also all the slope lines are below the function. Notice that. At this point here, we transition so that all the slope lines, even though they're positive, it's positive here, but now after I've gone through a derivative of 0 over here, that was the critical value, where the first derivative is equal to 0. It's a maximum there. The function is now decreasing here because now the slope lines are negative. But notice how all the slope lines on this portion of the domain are above the function. Okay, that's the change in concavity. And that's why we have a concave up function here and a concave down function. Okay, so putting all these together in one package, we can see that we can get at least some kind of idea of the behavior of this strangely looking cubic function without having to resort to plugging a bunch of numbers into the function and plotting each number individually. That would take a very long time. But also without having to resort to using some kind of computer. Maybe you don't have the computer right with you. This is a way to get some general basic idea of how the function behaves using the power of calculus and the first and second derivative tests.